So then last week we actually discussed about how the my molecules, my plane polarized light actually behaves in a composition of the two circularly polarized light. One is the left hand circularly polarized light, another is the right hand circularly polarized light. With respect to the speed of one particular circular polarized light, we actually find the optical activity of my molecules, and that is the optical rotation, which is we actually found in the what is polarimeter experiment. So another here basically what is we are talking about, we have something called, sorry, mm, plane polarized light we are talking about, which is actually combination of two. One is the right hand circularly polarized light, another is left hand circularly polarized light. LCP, and this will be my this, this will be my RCP. CP. Whenever we place some chiral molecule over here, let's suppose this is chiral molecule, solution of chiral molecule, chiral molecule, we have some difference of light. Let's suppose we are writing speed of light is different over here, and this one will be finished. This is not hampered to the, let's suppose the speed of light is different for each case. We'll have where speed of refracting index, speed of light L R not equals to. Then what will happen? Then we'll find the optical rotation. How? That left hand circularly polarized one. Initially with this one, this will be my that direction. In the case this will be maybe here, this may be here, this may be here. So finally resultant will get something like, the resultant will be our initial light will be this plane, and finally we'll get this is the final one, and this angle is called phi. This is called optical rotation. Okay, so now another phenomena where the one phenomena is that this is the one, another phenomena is that two, where the absorbance of one particular left hand circularly polarized light, that is A R, is not equals to A of is that L. This absorbance of left hand circularly polarized light and right hand circularly polarized light are different. In this case, what will happen? Let's try to find out. First, just summarizing it, and we have some problem. Later on, we'll discuss about this. So, our initial one is that two circularly polarized light, and either RCP over here. Oops. RCP over here, and then and LCP over here. Both absorbance is different. Let's suppose my LCP is getting more absorbed than the RCP. LCP RCP. Okay. And my molecules over here, we place the molecule here. Solution of optically active molecule which is absorb the light in that particular wavelength. And what we will find, this absorbance, the intensity of this one particular light will getting reduced. So let's suppose we are saying that LCP is more absorbed. So my RCP will be something like this, and LCP will be less in intense. So that means we have this one, and that will be my, let's say all the speed is equal to same. Well, oops, this will be right hand side, left hand. And let me finish. Okay. Okay. So what will the vector in this case? The vector resultant vector will be, let's suppose this will the overlap to each other, same direction. Here is that one, and this will be my another one, and then resultant will be in the black color. Here I am writing here. This will be the my resultant in black color, and then followed by the other one, my left hand circularly, right hand circularly is that amount, and this will be my, okay. Oh, let's draw the red first. Okay, and then this will be my resultant vector. It will be the resultant. Here will be the result. Okay, sorry. Uh, the direction will be different. This will be the resultant data, and this will be the resultant. This will be the resultant, and here will be the. If we combine together, then we'll get the one ellipse over here. This is the ellipse. Here will be the major axis over here. This will be the minor axis, and that angle, which is called psi. This is called psi. Ellipticity. Called ellipticity. This is the ellipse. Ellipse, and then this is psi angle is found in the ellipse. This is called elliptical motion only. Then this phenomena is called circular dichroism. This is called CD or circular dichroism. Okay. This psi actually can be denoted defined by some in our optical rotation, where we found in that here case optical rotation, this is the main thing. Here we have the initial one, this is the final one, this one is the phi optical rotation, and in circular by fringes, this is I'm denoting as a CB, not as a conduction band. This is the circular by fringes, and then in the CD, where circular dichroism, this is from the ellipse. This is the ellipse, and this angle is the psi. Is the ellipse, and this angle is called ellipticity. Okay, so this ellipticity, this is the angle. So we can mathematically derive some equation over here by using the tan tan psi, which is the tan psi equals to minor axis divided by major axis. Okay, so minor axis, why this absorbance is coming? So this minor axis, because of the absorbance is different, so that's why it is actually related to the absorbance of the air minus absorbance of R divided by absorbance of L plus absorbance of R. Okay, so as as psi tends to 0, so then tan psi should be tends to psi. So is from this equation we can say that psi equals to some equation is that 2.303 is a logarithmic term comes into the picture, so that's why 2.303 AL minus AR 180 by 4 pi, which is actually in degree. Okay, so here we can say psi is proportional to absorbance of different absorbance difference of LR and AL and AR. So which is basically proportional to delta absorbance. Now Lambert-Beer's law, from the Lambert-Beer's law, absorbance equals to epsilon C L. You know all those things. Now if we denote it in a one particular circularly polarized with respect to the one particular circularly polarized light, then this absorbance of left hand circularly polarized is actually denoted by, this will be the same for every cases. Only changes is that the interaction between the light and the molecular property is the only major thing. So this is the epsilon is the molecular property. So it will be the epsilon L, and other thing remains the C and L, and absorbance of R right hand circularly polarized will be mine, epsilon R C and followed by L. So from here we can say this delta A can be written as a delta epsilon C L. So my psi is proportional to, as the C and L are the constant for one particular experiment. We can say these are the constants. So only thing is that psi is proportional to delta epsilon. This is the equation we finally got from the molecular property with my shining light. Okay, so this is equation. Now there is another term called molar ellipticity. Term is that molar ellipticity, which is denoted as psi cis. This is the molar ellipticity, which is actually related with the ellipticity, which is 1100 psi divided by c. Divided by c del. So which is actually 3300 delta E by delta E. This is the final data we get, and this delta epsilon is very very small. Okay, this is the equation we found. Okay, so where where we can find that, where my absorbance of the left hand circularly polarized light is not equals to observance of right hand circularly polarized light, which is actually give us the circular dichroism. Circular dichroism, and which is actually related with the ellipticity. And when my speed of light, circularly polarized light, is different with right hand circularly polarized light, then it will give us circular birefringence. which is related with optical rotation. Now question is, can we all these two things happens in a single time? Can be possible? Yes, it is possible. So when the two of two phenomena is happening in a simultaneously, then there is another thing which is optical rotation as well as the electricity. We actually found that molecular system. So how it will looks like, we have our one circular right hand circularly polarized light, which is over here, and left hand circularly polarized light, CP, and we have left hand circular LCP. We place the sample here in green color. Let's suppose both the phenomena happens in a single turn, chiral. Both the phenomena happen in a single way, simultaneously. And this will be my observed light. So smaller term. Okay. So this is and speed also very less. Well, finally we will get the resultant of our, let's suppose in a, which one initially was this black line. That's supposed to be mine, but we'll get the final result will be this ellipse with a one particular rotation. Oh, sorry, this should be confined in that circle only. Okay, so this one will be my this angle will be my phi, and this angle will be my psi. So both the combination can be possible. So both effect happen. Now, our question is, what is the physical phenomena which is actually present in our molecules, who is actually responsible for the this circularly polarized light can absorb in a different way. Let's suppose our left hand circularly polarized light absorb more than the right hand circularly polarized light. as well as the speed of the circularly polarized light is defined in one particular case. So what is the physical property which is actually present that creates the my helical motion of the light actually getting behaves in a defined way in that particular solution, when the molecules is actually absorbing or slowing down the our light speed of the light. So to check that, we have to think about what is the physical origin of optical activity. So physical origin of optical activity will be physical origin of optical activity. Okay, so how this is happening, as we know, we have some over here, we know the how the light is actually absorbed. So this is will be my energy. We have the ground state. E is the ground state wave function. We have the one electron over here. We are shining the light over here. H nu. We'll get the new excited state, which is excited state, and that will be psi electrons over here. So that's how this is happening. How this is actually related with the transition movement integral, as we discussed in a previous discussion session, where that transition movement integral tmi, which is actually denoted by minus infinity to plus infinity. We have our excited state wave function, and we have the operator. Let's suppose O operator. We have ground state, uh, ground state, ground state wave function, and followed by d tau. And this is small area, small unit, small volume of the small volume of the which is actually denoted by tau. So overall integration actually give you the overall volume of our total systems. So this is the transition moment integral, and this electrical transition, that is, let's suppose we have the only absorbance is happening over here. So this operator can be denoted by, this is the dipole moment operator, which is this is the dipole moment operator, which is when the only absorbance is happening, only absorbance. This will be the operator, dipole moment operator. Now, as we know, in the molecular level, what kind of dipole moment we can produce? This is the electrical dipole moment we are talking about. This is the dipole moment. This dipole moment actually associated with a different kind of dipole moments present over in the molecule. So one kind of dipole moment is that electrical dipole moment, and which is actually denoted by mu e. This is very, we have some positive charge over here, some negative charge over here. The dipole moment over here generates, which is actually called electrical dipole moment. Another dipole moment is that this is a very strong strong dipole moment. Second is that magnetic dipole moment. So which is actually denoted by mu m. This is very weak. This is some charge which is actually surrounding, rotating. They have some magnetic field over here, so that's how we will get that magnetic moment. This is very less because of the electron charge is very less, so we have a little bit of magnetic moment over here. And then this is very weak, very weak dipole, weak. Now third one is that quadruple dipole moment, electrical quadruple moment. So which is actually denoted by q. And how it looks like, we have some same charge at the positive, at the opposite direction, and which is actually connected like four charges over here, and they are connected like this way. This is the quadruple moment. We'll find in a nucleus. Nucleus is the major responsible for this quadruple dipole moment. Nucleus responsible for this quadruple moment. This is also very weak, very weak moment. Okay, so as it is very weak moment, we are not considering this is as a this is actually showing any responsibility for the electrical transition, that is the electron transition in, that is region, visible region UV and visible region. So so a major thing is that our here the major part of the, which is actually responsible for this is the magnetic dipole moment, which is actually we should consider, and the electrical dipole moment we should consider over here. So now my transition moment integral can be written as, transition moment integral TMI right now can be written as, one part is the electrical part, another part will be my magnetic part. So how it should be, we have my minus infinity to plus infinity overall integration. We have psi ground excited state, psi star, and there will be my electrical dipole moment, and this will be my psi ground state, and followed by d tau, small volume of part. Now for the magnetic part also similarly, we have overall integration plus infinity to minus infinity. We have my psi excited state, and this will be my magnetic dipole moment, magnetic dipole moment, and followed by ground state, ground state with function, and small volume. Okay, this will be my two part of the dipole moment. So now, as we know, this this electrical dipole moment mu e can be written as this electrical charge, as the one electron we are considering as the charge of the electron, followed by the distance of the one on a charge of the molecules, and the followed by the distance between the two charge particle. That is the R. See, this is actually carrying the vector, as the it is denoting as a distance. So these are actually in can be denoted in a r theta phi direction, as well as in three-dimensional space. We can write it as r theta phi coordinate system or Cartesian coordinate system, which is actually x, y, z. So these are actually are associated with x direction, y direction, and z direction. So from it we can say that in the Cartesian coordinate we can find the r. Okay, and this is this actually how you have the positive charge, we have the negative charge. So this is kind of line. This will form a line kind of like in a, let's suppose we are thinking about the z direction. So we should write it one more time. So we have positive charge, we have negative charge, the direction, we have our dipole moment will be like this. This is the mu e. Okay, now another thing is that our another part, which is actually this magnetic one, this magnetic moment part of this transition moment integral. So in that case, how we can write the magnetic dipole moment? This is the mu m. Okay, this is the mu m, which can be written, which is actually proportional to r cross p. R is the distance. Oh, sorry. P is the momentum. P is the momentum. This is the vector product. And how it looks like? Let's suppose we have some charge particle moving around in a particular direction. So with respect to that moving particle, charge particle, they are circularly generating a magnetic moment. In our classical physics, what we get? We have, let's suppose we have some molecule charge particle moving around this direction. So with respect to it, there is a magnetic field generates over here in that circularly way. Okay, so this is my electric dipole moment, and this one will be my magnetic dipole moment. And let's suppose it is in z direction. So this one will be the rc direction. Okay, similarly, as this magnetic moment actually associated with the r rotatory motion, which is this r rotatory motion, as the r is the over here. This also associated with the mu m, also associated with rx, ry, and the rz. Okay, so this is associated with the rx, ry, and rz. So how it looks like in another direction? Similarly, we are actually writing in a z direction. Let's suppose we can write it in a xy direction also. So xy direction, this is my three-dimensional way. I can write this is the y, this is the z, this is y, and this will be my x direction. So that is in the x direction. If we are considering the mu x, mu ex, direction, then it will be the on plane of paper, and the rotation rx will be the rotation on the plane of my screen, and then ry will be perpendicular the plane of my screen, and as well as the z will be the in this plane on perpendicular to the z direction. Okay, so this is the rz. We have something called rx will be, this will be my mu y, mu u with respect to y direction, and this will be my mu m associated with that, and which is actually r y. And similarly x also looks like, this is my rx, and this one my x direction, this is the mu e in the x direction, and this is my r direction. So these all phenomena when two magnetic moment, magnetic moment, and the electrical dipole moment combined together, how forms some helical motion. Let's think about it. Okay, so we have our electrical charge which is actually moving. Let's suppose in a z direction. We have our electrical charge which is actually moving in the z direction. Now there is associate with a magnetic field with it. So how total dipole moment, electrical dipole moment as well as the magnetic dipole moment combined together, how it looks like? This is rotating over here magnetic field, and this is the electric field coming together. Okay, so that means it's forming a helical kind of motion. Okay, so we have my electrical dipole moment, which is actually this direction. Sorry about my drawing. This is my electrical dipole moment. We have magnetic dipole moment in that direction. This is the z direction, and this will be my rz. This is linear, and this is the circular. So if I combine together, let's suppose this will be my mu e dot mu m. How it will looks like? One direction is go up, one direction is rotating over here. So it will form a helical motion. Okay, so this will be my resultant magnetic moment, which is actually called helical motion. Similarly, it also have its mirror image. This will be my another mirror image. This is the thing which is actually propagating in a certain particular time. Okay, so in our molecules we have let's suppose one isomer have a helical motion of this left side helical part actually majorly predominant in a one particular molecule, and another particular enantiomer have right hand circularly uh, helical motion of the magnetic field and the electric combination of magnetic electromagnetic field in the molecular itself. So now if we shine the light which is actually circularly polarized, that means we have the plane polarized light which is combination of the two circularly polarized light. One is the left hand circularly polarized light, another is the right hand circularly polarized light, which is actually interacting molecules which having itself a this kind of helical electrical and magnetic dipole moment. Okay, combination of electrical and helical motion inside that molecule. So that these things actually interact to each other, and and once it's slowing down the speed of the light, one particular circularly polarized light, and one is that go through as it is. In that case, if slowing down, then it show the optical rotation. If it is absorbing, then it will show the my circular dichroism, that is the ellipticity will found. So we have a molecule. Now major funda in the molecular level, if you think about it, we have a molecule which have this helical motion in a one particular, see, if every polar or molecule have a some kind of helical motion, but in a symmetric molecule they have the both this left hand circularly helical motion, right hand circularly helical motion comes in a same amount. So they will cancel each other, then not cancel each other, they will absorb similarly in the left hand circularly polarized light and the right hand circularly polarized light. In that case we'll find nothing, there is a CD inactivity as well as the optical inactivity. Okay, but if one molecule which is actually chiral, they have, if chiral molecule is present, they have this one kind of helical motion is predominant over there. Let's suppose one enantiomer is actually having the helical motion of molecule itself having the dipole moment, helical motion of this left hand circularly helical motion. Then this should interact with the my incoming circularly polarized light. Okay, so in that case we'll able to differentiate. We have a helicity means we have a something kind of uh, chiral environment. We have helicity, we have the chiral environment, light is also chiral environment, and we have a molecules, we have a that the helical motion which is also chiral. So they will distinguish these two molecules, one isomer A and isomer B. We have a environment which is light, the environment is chiral, we have the some chiral molecule is coming into it, so that will form the diastereomer kind of thing, diastereotopicity will be there, and then diastereotopic environment will be there. So in that case all those systems properties of those systems will be behaves in a different way. That's why we'll able to differentiate, this is the enantiomer A, this will be the enantiomer B, and then we can able to detect that this is my molecules. Okay, so for that we, in that presence of this helical motion when will be present, that will be actually depending on some mathematical term we actually initially generated, which is that our, this is associated as it is associated with the xyz. So mu e, which is as it is associated with the x, y and z, and mu m, which is associated with the rx, ry and the rz. Okay, so one of them if present were there in a simultaneously, then our molecule can be CD active. So if one direction, this combination are active together, then our molecule will be the CD active. if molecule having one of them, that is the Rx and X, which is actually active in a in a particular certain point, then it will become the CD active. So my certain criteria should be they may be active together also. That will be the different case. So active together, the mu m and mu e should be active together at least one particular direction. Okay, which is creates which creates helical motion. Okay, so if a chiral molecule is there, then they have the helical motion of both. And that it is a chiral molecule, they have the left hand circularly helical motion as well as the right hand circularly helical motion forming together, and they are not differentiable in particular. So that's why in the raceming mixer we have the equal amount of left hand helical motion and the equal amount of right hand helical motion for um, a raceming mixer. In that case, we will not find any optical activity, and for that you will not able to detect the CD spectra if that is the receiving mixer. And we have, if it is there is one combination is greater, one enantiomer is higher, then it will have the some differentiate of the helical motion, and then we'll able to detect by the optical activity as well as the CD spectra. So now my transition moment integral, which is should be 0 or 1. If 0, that is the forbidden. If 1, that will be my that will be this will be the allowed transition. So transition, now another interesting part is transition moment integral. So now we are coming to the point group with respect to which point group actually active for the optical activity. So to come into that, we have the transition moment integral, which is over here. Transition moment integral, which is associated plus infinity to overall space minus infinity to plus infinity e of excited state. This is my operator and this is my ground state. Deta, it should be 0 or 1. 1 when this is allowed, and this will be my forbidden transition. Okay, so now in the character table, so this is the, let's suppose this is the function of orbital, this is also function of orbital. Now if you look into the character table, if there is some orbital actually coming into that, in the character table of the molecules, if you have the one point group, they have a one molecules. This molecule, let's suppose we have a one character table of a molecule, which is actually for the Rx, Rg, and Ry are combined together in one particular operation, in one particular orbital operation, in one particular orbit. So electronic transition, we are talking about electronic transition. Let's suppose we have uh, one molecule. Let's suppose now coming to the one example over here, where we can say this X and Rx y and ry and g and rg, one of them should be active in a one particular orbital. In that case only we can find the molecule will be optically active, and that should be CD active. Because of the for the CD active we need the, we have to, molecules should absorb the light first of all. Second thing is that there should be helical motion. To check that optical absorbance is possible when the x rx, when this kind of orbital is present, then we can get that. If there is a some magnetic moment associated with that particular orbital, from there this transition, this in that transition we have, we can say that that is the CD active transition can be possible in that orbital. Okay, so now coming to the one example. uh, if okay, so now coming example is that we have one point group. This is my point group. Okay, so this example is that that point group is, this is the character table of a D4H point group. This is the character table. This is the character table. You will find in internet. You can find it. I got it from the internet. So this is character table for D4. Sorry, D4H point. So can we can suggest the molecule? Yes, we can suggest one example of this point group molecule is that this is the iron tetracarbonyl chloride Fe, and which all are in all are in transposition, trans iron cell CO, sorry, CO, and we have CO over here, we have CO over here, and Cl, so this here, this is D4H. How do you know this is the D4H? First of all, how you can say? First of all, is it D4H? Okay, now check linear. We have a easy suggestion. Linear, no. Cubic, no. Cn, it has a C4 along with this FeCl Cl. Cl FeCl. This is the direction, Z direction. C4 is that. Is there any C2 perpendicular to the my C C4 axis, or C2 perpendicular to the C4? Yes, all are is this direction over here, this direction over here, this direction over here, this direction over here. We have the four. Now it is in D right now. And is there any H? Yes, it also have the H, which is actually over this plane, which is actually bisecting this FeCl Cl FeCl direction. So it is sigma H. Yes. So we have D4H point group. Now our interesting part is that our focus is that where the rotation or any translation, rotation or linear rotations or anything which is actually for one particular orbital. This is the orbital we are talking about. This is the orbital In that particular orbital, in one particular orbital, is there anything anywhere that this linear rotation, which is where the rx or r or in associated with that direction the x is active or not? Okay, in that case you can see here we can find the rg over here, but rg at a2g, which is active, and but z is active over a2u. One is active in a2g, another is active in a2u. Both are different orbital. So one case our magnetic moment is active, another case, another orbital, my electrical moment, dipole moment is active. So in that case we cannot so get the any optical activity, optical absorbance with the CD activity. Circular dichroism we cannot find because of this. There would be no helical predominant helical dipole moment, helical motion over there. So similarly, rx, and let's talk about the rx and ry. We have the eg, the orbital, that eg orbital we have rx in this eg orbital, we have the rx over here, ry over here, but eu associated with the x and y. That means we have one orbital contains rx ry, another orbital contains the xy dipole moment. So here also there is no such orbital is present where this r and the associated with that direction electrical dipole moment is active. So we can say there is no option or orbital where x, r, and the and associated with the mu m and mu e active in one particular direction. So which denoted that no predominant, no helical motion. That means CD inactive. Okay. Now, so what are the possible point groups? So as we know, we we actually discuss in that where the point group actually associated with the chirality, all those things. Where we say that we talked about that only the point group having the CN or DN point group, those are actually active for my CD activity. Okay, and the optical activity. Now another is that a molecule is that iron glycinate. Okay, so this is the compound. This is glycine, COOH. This is NH2, and here is the hydrogen. Okay. So this is the ligand. We can shortly denote it as O and N. We have the iron over here. In O, in O, in. This is the iron glycinate. So let's try with that. Is there any what is that? Is there any C3 or not? D. This is the D3 point. This molecule is D3 point. Okay. So D3 point group. Let's talk about its character table. Its character table. Let's suppose this is the orbital A1, which is actually the linear motion. We did not find any linear motion in A1. Now coming to the A2. Okay, A2, where you can find this A2 orbital RZ and Z, and in E orbital you can find RX, RY as well as the XY. Okay, so here you can see that in the A2 orbital, let's talk about A2 orbital, where we are finding RZ as well as the Z. So RZ associated with the mu M, which is actually Z direction, and followed by Z associated with the mu E at Z direction. We have this A2 orbital is now both combination have the mu M and mu E and mu M are active. Similarly, in case of E also, we have Rx active associated with X active, now and followed by Ry and Y. So that also sim mu M and mu E are active together. So it will provide the helical motion, and then this molecule is CD active. Okay. Now similarly, you can also find in a different point group where you can let's suppose D4H we have seen C4V, DND, all those point group. You can check that there's is there any chances of that Rx and Ry actually active in a certain particular orbital or not. You cannot find any here except that Cn and Dn point group. In that case, only we can find the optical activity and CD activity. Okay, so now we actually able to see how my optical activity associated with the helical motion, and this helical motion will actually interact with the helical left hand circularly polarized right and right hand circularly polarized left, which is also a helical in nature. Okay, so those are that's why they are interacting to each other. Now question is how my optical activity or optical rotation and the my CD spectra looks like. Okay, now have coming back to my initial part, you can change it over here. Okay. Now so Our fundamental factor is that molecules should be chiral, then it becomes the, first of all, CD activity, optical activity, there should be optical, okay, optical rotation. Second point will be mirror image with non-superimposable. Non-superimposable. Third point is that there should be no SN, no SN axis. So that means this is also associated with the I and the sigma. So I means my S2, sigma means S1. Okay, this is the fundamental factor. For the CD spectra, as we know, my X are X, Y are Y, and Z are Z simultaneously active in a one particular orbital. Then it becomes a optically active. Okay, so that much we actually cover. Now coming to the how my optical rotation and the CD spectra looks like. Now coming to the optical rotation. Okay, optical rotation. This phenomena actually monitored by the scientist called Cotton. We know the Cotton book in organic chemistry. Cotton book. This is which is actually Cotton. This Cotton actually helping out. Uh, that is the optical rotation, which is called circular bifringes. Phenomena is called circular birefringes. Okay, so where my speed of the light is defined in particular circularly polarized light. Okay, and now how it looks like if we take a different color over here, it's black. Okay, this is the lambda wavelength. This is the absorbance. Well, let's suppose my molecule is something, absorbance is, okay, this is my absorbance of the solution phase, and how CD or the, in case of phi, how can be here if for the in here now, this is the negative direction, this is the positive direction. How it looks like as it is absorbed 0 over here. Let's suppose this is the absorbance maximum over here in the, can say this is one molecule actually, one isomer actually. So CD optical spectra like not the CD. This is the optical rotation value. And another molecule, another enantiomer, which is the mirror image of each other, exactly give the mirror image to each other, and which is actually opposite direction. Sorry. Okay. This point is called the maximum absorbance is happen. This phenomena is called cotton effect. We have a one enantiomer. We can, with respect to the wavelength, if we check the optical rotation, then we'll get this kind of data. This is called cotton effect. Another isomer also give the opposite direction. Okay, so opposite to each other, and this particular, very interestingly, this particular region, which is actually called plane curve. Okay, this plane curve, where generally in our experiment, let's suppose we have our sucrose solution, where we are actually checking that how sucrose is actually degrading with the influence of the acid. We actually monitor by the polarimeter. By we have a sodium D lamp, which is actually around 560 nanometer region, and my sucrose solution is colorless, so it should not absorb the in that region. So if there is no absorbance, so in that case we will get only the plane polarized light will the rotate over here. So because of the non-zero value of the this phi non-zero value in that particular region. Okay, this is called optical rotatory dispersion. This phenomena is called optical rotatory dispersion. Now, another interesting is that now this is called, this effect is called, let's have a blue one. This is called positive cotton effect. If the curve going initially is negative direction, it starts again going to the positive direction. It is called positive cotton effect. On other hand, the reverse one is called negative cotton effect. This is called negative cotton effect. Okay. This is positive cotton effect. Okay. Now, this is the optical rotation. Now, coming to the electricity, which is actually associated with that. My what is that? Circular dichroism. Second is that electricity, optical rotation. We talk about electricity. So, let's suppose we have absorbance, similar curve over here. This is the absorbance lambda. This is the absorbance. We have something called ellipticity over here only. Over here, this is psi. Molar ellipticity we are talking about, which is actually proportional to absorbance of L right hand circle. Okay, so now my absorbance is similar. Let's suppose this is the my absorbance. Let's suppose this is a perfectly Gaussian curve. No, this is not actually perfectly Gaussian. One more time, I am drawing it. And here is the maxima. In the ellipticity part, in the ellipticity spectra, how it looks like, one isomer actually give you this kind of similar data. Okay, and another isomer actually give me the exactly opposite of that mirror image of this spectrum. And interestingly, there is a observance 0 over here. 0 observance is equals to 0. Why this is so? Because of, first of all, in UVBs there is UVB spectra, there is no observance over here. Oh, sorry, this will be also similar. Exactly over here, similar as CD as UV similar. Only is the direction will be different for one particular enantiomer. So their absorbance is 0 because of molecule is not absorbing in that particular direction. In the CD spectra, it is actually associated with the molecule should absorb the light, the left hand circularly polarized light or right hand circularly polarized light. Depending on that, we actually get this CD spectra. If molecule is not absorbing anything, so how we can say that this is the my CD spectra, where the CD spectra which is actually active in that particular wavelength. So first of all, molecule have to absorb on that particular wavelength that should match the transition where the electronic transition can happen, and then it's supposed to be in that transition the magnetic moment will be active. So all those we actually covered. So this thing is that we have our uh, this is my uh, where the absorbance is 0, my CD spectra also show the same 0. Okay, now if molecule have some CD spectra, UVB spectra is a different. Let's suppose there is a one Gaussian curve. We are showing here only one Gaussian curve. If there are multiple shoulder kind of Gaussian curve over there, then how it should looks like? It may be different in particular case. Some of them may be active in CD spectra. Some of them may not be active in CD spectra. So one example is that we have some molecule having UVVs of, this is Last example over here. Lambda, then absorbance over here, and let's suppose our UV structure is, this is something like called solder over here. What's- okay, this is the my UV structure. Okay. And how the CD will be, let's suppose it's possible that four band is active in CD because of the four transition actually happening in a one particular one particular orbital, or a different particular orbital where the RX, RY, RZ all are active over there. But in some case may not be all four the transition is not active in CD spectrum. Let's suppose over here this is this part only active in CD spectrum, active R and XYZ all are over here only. So in CD spectra, it should looks like one enantiomer will give us, let's suppose one enantiomer is giving me this. I'm very facing difficulties the my drawing. Oh, no. Okay, and this is the my CD one isomer, enantiomer, and and another one is that exactly mirror image of each other. Okay, so this is mirror image of other one. Okay, this will be my enantiomer two. Oh, forgot to write. This will be my molar electricity, and this will be my lambda. Okay, so it may be possible that one on one direct one transition is in positive direction and the transition is negative direction. In that case, we will get this kind of data. I'm writing it in a dotted line. So this is the color blue. So it's maybe possible of that. This is another one. It's maybe possible. This transition may be this one also maybe looks like this one. It may be possible depending on that which transition is actually show that kind of CD activity. Okay, positive electricity or negative electricity. So far we actually covered that how CD spectra looks like. Now in that in that session we actually covered how the origin of optical activity comes into chemistry in features in the molecular level. So the light, how the phenomena is happens. If circularly polarized light absorb the light, then it will form a electricity. If circularly polarized light slowing down one particular molecule is slowing down the one particular circularly polarized light, then we'll able to get the optical activity. And if molecules absorb one particularly circularly polarized light, then we will get the ellipticity. And that ellipticity actually can be defined by the uh, defined by the difference between the molar extinction coefficient of of that optical one part optical optical molecule, for that uh, epsilon r and epsilon l are different. That value is very low. So, and some case for the both happens. One is that if molecule actually slowing down the optical slowing down the one particular rotating circularly polarized light, as well as it's also absorbing one particular circularly polarized light, so that in that case we'll get the both effect combined together. We get the ellipticity as well as we get the optical activity, optical rotation also by of plane polarized light. Okay, so that how next we actually discuss about what is the molecular property which is actually interacting this circularly polarized light. To find that, we actually go through the molecular level where we find in the molecules we have some defined kind of dipole moment. One is that electrical dipole moment, another is the magnetic dipole moment, and another is the electrical quadrupole moment. But this electrical quadrupole moment, which is actually maybe generally found in nucleus, which is very less, and uh, which is can be negligible. But magnetic dipole moment is very weak, but it has some value over here. These small changes can also affect some different activity. So major strong part is that electrical dipole moment. And to check that, we have the electrical dipole moment, which is associated with that in the Cartesian coordinate. We have one particular direction x, y, z, any here, or combination of all those direction. And magnetic dipole moment, which is associated with the r and the momentum. And if one charge particle actually moving towards one direction, any direction, with respect to it, it's perpendicular to that charge moving. There is a circular motion which is formed. There is a magnetic momentum which is actually produced, which can be denoted by the Rx, Ry, and Rz, combination of those or one particular direction. And to check that this combination of the electrical dipole moment and magnetic dipole moment, it will form my helical motion of the molecules. Okay, and the helical motion, when the helical motion comes into the picture, if that molecule in a one particular orbital for my x and rx, y and ry, z and rg, at least one particular combination should be there. And then in that time, the mu m, that is the magnetic momentum, magnetic dipole moment, and the electrical dipole moment active, and combination of those will form the helical motion. Now, question is that we have dipole moment of is that we have the asymmetric molecule. We have a dipole moment. We have a magnetic moment associated with that. But this molecule is a symmetric chiral molecule. Achiral molecule is a symmetric one. It also has another dipole moment, which is actually opposite to it, because of it can cancel to each other. And then and mirror image of it, as it is one, it pass through a one mirror image of that. So one helical motion, with associated with another helical motion equal amount with equal intense. So that's why a chiral molecule is not show any CD activity or optical activity. CD and optical activity, optical rotation activity. So to that we gone through some character table for the different point group, which is a D4 range. In the D4 range, where we found there is no combination, no orbital where the this combination is valid, where the X, Rx, Z, Rz, or Y, Ry is actually present in a one particular orbital. So D4 is, so that's why D4 is a chiral molecule as well as. So there is no helical motion. So if there is no X Rx combined together, or X RZ or Z or RZ, and Y and Ry combined together, active together, then there is no helical motion. That means my molecule is inactive. Molecules in CD inactive. So one example is that iron tetracarbonyl chloride. Okay, and this is a D4 H point group. Now we have another example is the CD3 point group, which is the iron glycinate complex, which is D3 point group. But we can find that two orbitals, like A2 and E, which associated with the Rx and Ry, Ixy, both combined active together, and A2 actually active for the Rz and Z combined active together. So that means we have the magnetic moment, electrical dipole moment, as well as the magnetic dipole moment combined together. They can make a helical motion. So that helical motion actually give me my CD activity, because of that interact with my LCP or RCP in a different way, and as a result we can get the optical activity as well as the CD activity. Okay, so next we actually discuss about the how optical rotation and the cotton effect, which is actually associated with the absorbance of my molecule. For the absorbance is maximum absorbance we get. In that case, the in the cotton effect we will get the zero high value because of the optical rotation, because of in that region all the lights actually absorbed by the molecule. We did not get any data, and most of the optical activity actually measured in that region where the my molecule is not absorb any light. That is the best way to monitor the optical rotation. And we again here we found the positive Cartan effect and the negative Cartan effect. Positive Cartan effect and a Cartan effect comes into picture in case of circular fringes, where the speed of the light, left hand circularly polarized light and the right hand circularly polarized light different. In that case, we can get the optical rotation, and we can get the Cartan effect. Now, the ellipticity, in case of ellipticity, where the molecule have mu m and the mu e active, and which is absorbing light around my UV's region, UV's and region. One isomer, if show the ellipticity of positive direction, the enantiomer, another enantiomer will give me the exactly opposite mirror image, that is the negative ellipticity it will give us. If molecule have some different, let's suppose some molecule have a huge number of transition over there. In that case, some of them may be optically active, some of them may not be optically active. So for that case, we can get one that transition which is actually CD active. That so which of them of my transition are CD active, that can be detect by the CD spectroscopy very easily. That structure of the UPVs and the CD may be different because of they are in one particular transition is, let's suppose here initially we said that both the transition of one enantiomer are in positive electric, so the positive electricity. It may be not possible, may not be possible. Let's suppose one transition is so the my negative electricity. In that case also we can get a different spectrum which can be easily monitored by the CD spectrum. To that, so I'll stop here, and the next session I think I will cover, try to solve some different research paper. uh, First of all we have to cover it, to know that how the CD spectrum professor also cover all those things. And I'm just recapitulating it. If you have any doubts, then come back in the next class. I'll let you know what is the problem you are facing right now. If nobody is there, so it's very difficult to say what is your problem and try to solve it. If you don't have any question, just if you have any question, just message me anywhere. You'll get the all the you can comment in my YouTube channel if you have any doubts regarding this the doubt solving session, or regarding any problem. If we find any comment or any YouTube channel, so I will try to solve that problem first, and then we'll go to further discussion about the problem, different problem, what problem we'll find in a different kind of exams like NET, GATE, exam. Exam doesn't cover this CD, so I will try to bring some problems in the next session. And thank you, and we'll be there in some next session. Okay, then bye. I'll stop here. We have the 7 minutes left. I will stopping over here only. We have finished my content today. Okay, stop sharing. Mm.